Welcome to this explainer. If you really stop and think about it, the way a neural network actually learns is a pretty profound mystery. You feed data into a system, it passes through millions, sometimes billions of parameters, and at the very end, it spits out an answer. If that answer is wrong, sure, you measure the error, but how exactly do you trace that error all the way back to fix the very first step?
Right, so this is the ultimate 1 to 100 puzzle. If your neural network is this deeply nested stack of 100 different functions, how in the world do you find the derivative of the loss for the earliest weights when that loss is separated from them by 99 other mathematical operations? It's a massive mathematical puzzle, often called the credit assignment problem, and it's absolutely central to deep learning.
Okay, let's dive right into this. We're going to cover 1. The credit assignment problem. 2. Visualizing the chain rule. 3. The autograd miracle. 4. Debugging failure modes. And 5. The domino effect.
Starting off with Section 1, the credit assignment problem.
Let's actually rewind a bit to see how this developed. Back in 1673, Gottfried Wilhelm Leibniz formulated the chain rule for simple scalar functions. But the sheer engineering necessity of it, well, that wasn't truly felt until the 1970s and 80s. Researchers were trying to train multi-layer perceptrons, and they just hit a brick wall. Adding a second layer created a composite function, and they were completely stuck. Then, in 1974, Paul Werbos published his thesis showing the chain rule could actually be applied backward through a network. By 1986, Rumelhart, Hinton, and Williams popularized this exact process as backpropagation. The crazy thing is, without this centuries-old math bridging the gap, modern deep learning literally cannot exist.
So that historical bottleneck they hit, that was the credit assignment problem. Simply put, it's the mathematical challenge of propagating a final loss signal backward to update the earliest weights in the system. Without a reliable mechanism to assign that credit, or blame really, we could easily measure how bad our final loss is, but we'd have absolutely no mathematical way to reach back and actually fix those foundational layers.
Moving on to Section 2, Visualizing the Chain Rule.
And this brilliantly illustrates what's going on under the hood. Imagine 3 processing stations, or nodes. Let's call them station A, B, and C. Picture a pulse of light, which represents our error signal. In step 1, that pulse enters the rightmost output node, station C. In step 2, the node basically asks itself, okay, what is my local derivative? Based on that specific answer, the pulse physically shrinks or expands. Finally, in step 3, the newly adjusted pulse passes left to the next node. Backpropagation isn't just dry math. It is exactly this, physical signal transmission passing backward through the entire network.
Mathematically speaking, this signal transmission is just simple multiplication. We're literally just asking each node for its local derivative, its local sensitivity. Let's say station C says, well, if you increase my input by 1, my output increases by 2. Okay, so its local derivative is 2. Let's say station B is 3, and station A is 0.5. The chain rule simply tells us to multiply them all together. A's sensitivity times B's sensitivity times C's sensitivity.
So 0.5 times 3 times 2 gives us a total sensitivity of 3.0. Now, why is this number such a game changer? Because imagine you're the manager and you see the final product from station C is exactly 10% too large. You don't have to guess how to fix it. You take that 10%, divide it by your total sensitivity of 3.0, and you instantly know you need to shrink the raw input at station A by 3.33%. Boom, you've just mathematically solved the credit assignment problem.
Let's look at Section 3, the autograd miracle. Now, what's really interesting here is the breathtaking contrast. Think about the actual math required for this in a modern neural network. Dense, multivariate chain rule formulas, partial derivatives, and transposed Jacobian matrices. It is incredibly, mind-numbingly complex. But then look at the PyTorch code. It's literally just law-stop-backward. That's the whole thing. That one single line of code is the autograd miracle. It is the automated, highly optimized execution of all that terrifying math. And this is exactly the moment you realize why we use frameworks like PyTorch.
So how does PyTorch pull this off? It uses reverse mode automatic differentiation. During the forward pass, it quietly traces a computation graph. The second you call backward, it enqueues at the output and traverses backward, accumulating all those complex vector Jacobian products node by node and storing them right in the .grad attribute. But the real miracle here? Efficiency. To compute the gradient for millions of inputs, this entire algorithm only costs roughly twice the compute of the forward pass. It is remarkably efficient.
Section 4, Debugging Failure Modes.
Let us slow things down for a minute here. When you are building a prototype and the system breaks, we have to approach the problem clinically. The systemic failures usually fall into a few specific categories. If your loss plateaus instantly, and the early layers simply aren't learning, you are likely looking at vanishing gradients caused by very small local derivatives. The clinical solution is often switching your activations to ReLU. If your loss suddenly becomes NaN, you are dealing with exploding gradients, where large derivatives multiply out of control. You need to systematically clip those gradients. And if you encounter a runtime error about variables being modified, you have used in-place operations. You've actively overwritten the exact forward activations the chain rule relies on to compute its backward pass. Use out-of-place operations instead to resolve this.
Let us take a clinical look at vanishing gradients. Visualize a bright, blinding light of loss entering the final layer of your network. If you're operating with 50 layers using a sigmoid activation, the maximum local derivative you can achieve is 0.25. As that bright light passes backward, it is multiplied by 0.25 at every single step. It gets progressively dimmer, layer by layer. 0.25 to the power of 50 is approximately 10 to the negative 30th power. By the time it traverses back to the first layer, the light is entirely gone. The signal has decayed to absolute zero. This is the precise physical reason why the model forgets the early layers.
There is another physical limitation we must frequently debug: the memory-compute trade-off. In order to calculate those local derivatives during the backward pass, PyTorch is forced to keep the entire computation graph, including all forward activations, in your GPU's VRAM. And that memory requirement scales linearly with depth. When you inevitably run out of memory, the standard solution is gradient checkpointing. You deliberately drop the intermediate activations to save VRAM, and you simply recalculate them on the fly during the backward pass. You are effectively trading raw compute time to bypass the rigid physical memory limits of the chain rule.
And that brings us to Section 5, the domino effect.
So, bringing our energy back up, the crucial point to take away from all of this is to simply think of backpropagation as a giant domino effect. The chain rule is literally just local sensitivities multiplied backward from the final loss to the first weight. If you push the first domino, it topples into the second, and eventually it hits the loss. To figure out how hard that very last domino will fall, you don't need to track the whole chain at once. You just ask each individual domino, hey, if I push you 10% harder, how much harder are you going to push the next one? You just multiply those local pushes backward. It's elegant, right?
But, as we look to the future of AI, there's a massive challenge looming on the horizon. We know that chain rule absolutely requires storing those forward pass activations. So, as large language models reach 1 million token context windows, the memory required to store all those attention activations for the backward pass is astronomical. It's a massive memory wall. How will the next generation of architectures overcome the strict physical memory limits of the chain rule? It's a fascinating problem, and the AI community is racing to solve it right now. Thanks so much for joining me on this explainer.